Today we're going to define standing waves. Here's a string, and here is a wave on that string. And let's fix the end to a wall. And as that wave moves, it hits the wall, and it's reflected from the wall. And we see it come back. And as it comes back, it will interfere with the original wave. So here's an animation of a wave approaching a fixed wall. You can see the particles move up and then move down, but notice that the particles are not moving to the right or left. They just move up and down. So you can even focus on one particle, and that particle is just moving up and down. And then as the wave is reflected, there are times where there's constructive interference, when we see a maximum, and destructive interference, when we see a minimum. And so as the wave moves through the medium and hits the wall, reflects, we get a standing wave, where it would just look like one wave vibrating back and forth like this. So when I remove the incident wave, the one that was coming in, and the reflected wave, I get a standing wave. So let's analyze the math of a standing wave. So here's a string. And if we've got some wave in the string, and that wave will either be up or down, so the other option is the dotted lines here. This is a node. So this place right here is a place where the particle, the medium, the string is not moving. Here is an antinode. So anti means not. So this is not moving. So this part moves the most back and forth. There's also an antinode here and an antinode there. There's a node here and a node here. So not moving means it's moving the most. The simplest standing wave would be if you plucked a string. So here's a string fixed on both ends. And this would be the vibration. We would see up or down. And if one full wave looks like this, then there's only this half of the wave in our string at any time. And if V equals F lambda, the frequency times the wavelength, and the wavelength is part of the length of the chord, the frequency will be speed over wavelength. And if the string is a length L, then there is 1/2 of a wave, so 1/2 of a wavelength in the whole length of the string. So that means the wavelength is equal to 2L. So we'd need 2 of these strings to get a whole wave. So then our frequency would be equal to speed over 2L. This is the first harmonic. Our second harmonic would have 2 loops, 3 nodes and 2 antinodes. Again, looking at this wave, I see one full wavelength in the length of the string. So if the whole length of the string is L, then in this length there is one full wave. So 1 full wavelength in this length of string. And if frequency is speed over wavelength, then the frequency would be equal to the speed divided by the length. That's for the second harmonic. So the frequency of the nth harmonic, so n meaning any number harmonic, so the first harmonic or the second harmonic, third harmonic, would be the frequency of sub n, meaning which one, nv over 2L. So let's see, so this frequency is the number of the harmonic. So that's what that little n stands for, which harmonic. The V is the speed of the wave in the string or whatever medium. L is the length of the string. Now it's going to be measured in meters. But we can check this. So let's see, the first harmonic should be F sub 1 equals 1 times V over 2L. And if you remember, that's the equation for our first harmonic. The second harmonic would be frequency sub 2 is equal to 2V over 2L. So I'm using this equation here and substituting in. The 2's cancel out and I'm left with V over L, which matches the equations that I had above.